Hello everyone. So this is our third lecture on quantum physics, and in our previous lecture we discussed about photoelectric effect and its applications. Okay, and today we will be discussing about one more important effect, that is Compton's effect. And you must know the basics of you can say photon and basics of mechanics for today's lecture, because in the derivation part we will need that. Even I'll also, you can say, give you a short revision for that concepts. But if you know earlier, then it will be very beneficial for you. Okay, so let's start our today's session. Okay, so the topic of our today's lecture will be Compton effect. Okay. Compton was the name of scientist. Okay, and he gave this effect, that is Compton effect. So it is named as Compton effect. Actually, the reason why we are studying Compton effect, first of all, it is a part of quantum physics. So we are studying. Second, the existence of photon, the experimental evidence of existence of photon, we get by this particular effect, that is Compton effect. Okay. So let's start the effect. Let's start this particular topic. So So there was a scientist named Arthur Compton. He gave this effect. This effect is mainly to tell us about the experimental. It is an experimental evidence for existence of photon using X-ray scattering of electrons. Okay, using an experiment, that is an X-ray scattering experiment of actually electrons, we get the idea about the existence experiment. This is an experimental idea for your photons existence. Okay, so what's the broad meaning of this particular broad idea of this particular effect, that we will discuss first, then we will go into the mathematical portion. Okay, so let's begin. No heavy mathematics is used here. Basic mathematics will be required. So what actually happened? We will have some cases where we will consider, um, you can say, two phases, or you can say there are two segments. First will be the before collision, and second will be after collision. What will be the collision? So see, we'll have a photon, or you can say a light ray, that will consist of a photon. Now this photon and electron will undergo collision, and finally what happens? This electron moves out with some momentum and some momentum with some kinetic energy and momentum. So we will take some of the, you can say, we'll introduce you with some of the terms, and then we will proceed towards this mathematical portion. So let me first give you a brief revision for the formulas of energy of photon, and then we will discuss about two laws. Here we will be, you can say, using two laws, that will be law of conservation of momentum and law of conservation of energy. I'll first tell you the basics of it, then I'll start with the derivation portion. Okay, so let's begin our basics. Okay, so uh, first of all, energy of photon we all know in terms of reduced Planck constant. See, we have discussed in terms of Planck constant also, but you can say we'll use it in terms of reduced Planck constant most of the time. So H cut into W, or you can write it as in terms of lambda also you can write. no issues. But here this is more important. Then one more thing, momentum of photon. So momentum of photon, that is pp. This p subscript tells us about the photon. You can write also here for no confusion, that momentum of photon. So momentum of photon, we discussed that it is energy of photon over speed of light. So we'll just use this h cut w by c. So what it will be? It will be h cut, and this w by c is a constant, that is a wave constant, or you say it's a wave vector, or you can say it's a propagation constant. Okay, so there are several names for this scale, but for the sake of convenience, we can consider it as a wave constant, wave vector constant. Wave vector constant. This vector is important here because we will use it in the derivation portion, the essence of vector. H cut into k will be the momentum of photon. Okay, and the energy of photon we discuss is h cut into w. Now, we will discuss two laws, that will be law of conservation of energy and law of conservation of momentum, and then we will start our derivation portion for this particular Compton effect. Okay, let's begin. So, first of all, recall the law of conservation of energy. What does it say? Total energy remains conserved, okay, in isolated system. So you can say that total energy change in total energy will be constant. It means you can write it as final total energy minus initial total energy, and this will be 0. So we can write it as total final you can say final total mechanical energy after collision and before collision. This will be equal. This final means after collision. We'll discuss the collision portion of collision also, and initial is your before collision. Okay? In that terms we will take. So this is your total final energy equals to total initial energy. Okay, we will use this particular concept, law of conservation of energy. Now, law of conservation of momentum. Momentum. So what does it say? Net momentum remains constant. So delta p net is equals to 0. So p initial equals to so just total, you can say total is net only. P net initial equal to p net final. Okay. Now let's start our derivation. So we will consider two cases. First is your before collision, and second will be your after collision. What happened? Okay. So before collision, we will deal with two particles, that is electron and photon. Before and after collision. So before collision or after collision, Planck constant will remain, reduced Planck constant will also remain, no issues. Before collision, for photon, you will say W will be its angular frequency, and here W dash will be, you can write Planck's constant, reduced Planck constant. Okay. So W dash will be the angular frequency, final angular frequency. This is the initial angular frequency. Okay. For photon, W and W dash. Fine. Now for electron, what we can write? It is initially at rest. So we will use this initially at rest. Okay. And for electron here, uh, performs motion. So let's start and we will understand step by step. Okay, so let's begin. So first, using using law of conservation of energy. Okay, so total final energy, total mechanical energy after collision, total mechanical energy you can say before collision will be equal. So writing this. Okay, now total energy will include the energy of photon after collision plus energy of, especially kinetic energy of electron after collision. Same here, EP initial plus K initial of electron. Now initially it was at rest, so 0. And now this Me, we will use Me for mass of electron, okay, and Pe, momentum of electron, MOM dot momentum, okay. So EP final minus EP initial is equals to what it is actually, is minus of K of final, I think. You can write it in this way also, EPI minus EPF is equals to KEF of electrons. Okay, now just write the in terms of reduced Planck constant of photons energy, and here you will use the relation between momentum and kinetic energy, that is P is equals to root under 2 m kinetic energy, that we will use here, that will be P square PE square by 2 m. Fine, and here you will write H cut into W minus W dash. Fine, I hope it's fine. This is our first equation which we'll be using after some time. Okay, H cut into W minus W dash is equals to P square by 2me. Okay, note this equation. We will move to the next segment. Now, using law of conservation of momentum, I'm writing it M, law of conservation of momentum. What we can write? Final momentum, net final momentum equal to net initial momentum. So final momentum of electron plus final momentum of our photon, okay, will be equals to initial momentum of electron plus initial momentum of photon. Yeah. Now, initially it was at rest, so momentum will be 0. No issues. Fine. Now this final momentum of electron and this which we are using, we have discussed also the, what do you say, momentum of photon, that was H cut into K. Fine. So let's use that. Pi minus Pf or photon is equals to P final for electron. Okay, we will use it as P. Fine, and here you will use that H cut into K minus K dash. This is our second equation. Okay, I hope it's clear to you. Okay, just have a look on this. H cut into K minus K dash, we have discussed. If you have not, if I missed, then here we are discussing K is your initial wave constant and your K dash is your final wave constant. Okay. So we have taken H cut common and then we have just uh, reduced to this. Now we will use this particular second equation and putting the value of PE from second in first. Okay, so uh, let me rewrite the equation. There it was like this, 2m. Just put this H cut square K minus K dash square over 2m. H cut W minus W dash, H cut here. Okay, now W minus W dash is equals to H cut by 2m k minus k dash whole square. Now, to proceed from here, you will have to use some, you can say, concepts of vector and consideration of vector as scalar too. So, first of all, note this equation. We will use it. Now see, this k minus k dash, this k is a wave vector constant. Since it is a vector, we will use rules of vector. Okay, see, we have discussed or you may have studied that if we are writing a minus b vector and we are writing it's a square, then what it is actually mod a square mod b square plus 2 sorry minus here minus 2a dot b, that is ab cos theta only. We will use that particular concept here. Okay, so just have a look. W minus w dash h cut by 2m k square k dash square plus 2k k dash cos theta. Fine. Okay, now w minus w dash is equals to h cut by 2m. Now here you have to consider this k and k dash as, you can say, we'll consider its magnitude only. Not actually, I'll say we'll consider it as a scalar, but we'll consider its magnitude here, and we will use the simple algebraic formula that we use, that is a plus b whole square, that is a square plus 2ab plus b square. That a square plus 2ab plus b square, that will be the you can say we consider k and k dash as a and b. So you have to write it in this term, k minus k dash. Here we will use a minus b whole square, the same algebraic plus minus, and 2k k dash 1 minus cos theta. Now you just check. Now here we have considered k and k dash as a scalar. Once you consider this, you will reach to this equation, k square plus k dash square minus 2k k dash. Here plus 2k k dash both will get cancelled, and minus 2k cos theta you will get the same as you were with above. Now this k minus k dash is very small. This value is very small. K is again value small, k dash is very small, so the product there, you can say subtraction will be very small. So we will just ignore this particular value. W minus w dash is equals to h cut by 2m 2k k dash into 1 minus cos theta. I think this is the required one, so 2 get cancelled. Now what we have to do, just we have to divide this equation, w dash 1 by w dash minus 1 by w is equals to h cut by m. Now here you have to look k by w dash, sorry, k by w, k dash by w dash, 1 minus cos theta. Okay, now one thing you have to understand, that v, we are writing v, or actually here we are more concerned about photon, so we'll use its energy, its speed, that will be c. So that we will use w by k is equals to c. So just look this particular equation first, then we will use that one also. What is this? 1 by w dash minus 1 by w is equals to h cut by m, k by sorry, w by k, or k by w, it's k by w, sorry, wait, I have to erase this, k by w, k dash by w dash into 1 minus cos theta, right? Here I write 1 minus cos theta into, okay. So uh, we know this particular relation, that is c is equals to w by k. You can check by dimensions also, or this is the general which we know about the wave. Actually it is for v, but here this is c because we are here concerned about photon speed. So this will be your 1 by c, 1 by c. Okay, so we will write this 1 by w dash minus 1 by w equal to h cut by mc square 1 minus cos theta. Fine. Now we can write it in terms of wavelength also, no issues at all. That will be, you know this particular relation, you know this. So to express this in terms of wavelength, we know this W by K is equals to C. Okay. Now we also know that W can be written as C into K. This K is actually 2 pi by lambda. Okay. So we will use this particular expression here. Okay. So just use. So 1 by W will be lambda by 2 pi C. Fine. 1 by W dash will be lambda dash by 2 pi C. Fine. So just write this. Lambda dash by 2 pi C minus lambda by 2 pi C. Okay. So it is h cut by mc square 1 minus cos theta. Now we will take 1 by 2 pi C common. Lambda dash minus lambda is equals to h cut by mc square 1 minus cos theta. This C get cancelled. Now lambda dash minus lambda is equals to 2 pi h cut by mc 1 minus cos theta. So hopefully we are on the correct expression. Yes. So now this is our expression in terms of this lambda dash is your you can say final wavelength after collision of photon. This is lambda is the initial wavelength of photon. This h cut is reduced Planck constant. 2 pi is a constant. M is actually here me. We can write mass of electron. This C, this particularly this C is the energy of photon. Speed of photon. Okay, this theta is the angle between K and K dash. We can write these expression also, but we will convert it into more simpler form. This 2 pi h cut is what? H cut is actually h over 2 pi, so you can write this as h by m c into 1 minus cos theta. Fine. So this is your expression. So lambda dash is your final wavelength of photon after collision. Lambda is initial wavelength of photon before collision. Okay. Then we have what? H cut is your reduced Planck constant. C is your speed of light or a photon, and the theta is the angle between K and K dash wave vectors. K and K dash wave vectors. Fine. So let me rewrite the final expression which we got. That was in terms of wavelength we are writing. Okay, because we have reduced it to terms of wavelength. So lambda dash minus lambda is equals to h over mec 1 minus cos theta. So this is our expression. Okay, and this is actually the mathematical interpretation of Compton's effect, which we discussed was about the existence of photon. On an, See, I have not discussed with you the experimental setup and all, but it is an experimental. See what happens actually when we say we are on the way to find the evidence of existence of photon. Then we know the properties of that particle. Now we will just match up it with the experimental results. If it is matching, then we will say yes, it's photon. Like electrons discovery by J.J. Thomson was also an experimental process that something you can say particle was you can say seen to be attracted towards the positive plate. So we say it is an actually negative charge. It was named as electron. So actually, the properties, the visible properties, the visible behavior of that particle, you can say sets as, or you can say builds a foundation to just get the experimental results or get the evidence of its existence. Okay, so this was all for our today's session. The next session we will discuss about atomic models. That will be a I'll give you a brief about Rutherford and Thomson model. Main we will discuss about Bohr model. That is very important. Okay, and that is the main you can say crux of this atomic models. Okay, so thank you so much for joining me in this session. Next session will be on atomic models, lecture number 4. Okay, thank you so much. Bye bye. Take care and exiting 1, 2, 3.